The following is a conversation with Chris Miller. Chris is the Assistant Professor of International History at the Fletcher School of Law and Diplomacy at Tufts University, a Jeane Kirkpatrick Visiting Fellow at the American Enterprise Institute, and Eurasia Director at the Foreign Policy Research Institute. Chris's work examines key shifts in international politics and economics, and his 3 books so far are titled, respectively, Putinomics, We Shall Be Masters, and The Struggle to Save the Soviet Economy. So you might have guessed there is a theme to his books there. Chris is an expert on Russian modern history, particularly economics, and therefore an unlikely profile to have become one of the journalistic authorities on the semiconductor industry. Maybe not the industry, but certainly the history of the semiconductor, which, by the way, is just jargon. It's synonymous with microchip, computer chip, semiconductor. They are, for our functional purposes, the same thing. So Chris is in the process of publishing his next book, which is precisely on this topic, the big bad political history of the computer chip. And as we sort of touched on in the chat, little did he know when he embarked on this project well before 2021, when supply chain constraints would bring forth to public consciousness the wonderful complexity and importance of semiconductors, that it would become such a popular and spoken about topic. It was in the heat of that 2021 supply chain constraints that I myself became really interested in the industry and went to ASML and spoke with Jos Benschop, who's the Vice President of Technology at ASML, someone who Chris knows now that he's been doing his research. And some of you might remember that interview. It was at number 56. And it was actually upon that, it was our mutual admiration for the company ASML that we became connected. I saw Chris feature in a podcast speaking about the supply chain of the ASML EUV machine specifically, and reached out to him after that, and I'm so happy I did because, as you will see, this podcast is an absolute masterclass by Chris Miller. Yourself and I, dear listener, we get to sit courtside as Chris really takes us top to bottom, the wonderful complexity of this irreplaceable technical marvel, which is the microchip. In this podcast, you can expect to hear about some of the following: an explanation for the complexity in construction of a semiconductor. Jos made the claim that the machine that he was involved in building, which is an irreplaceable part of the construction of a semiconductor, was the most complex machine ever built by humans. And Chris doubles down on that in agreement. We speak about why the supply chain is so fragile. Why can't the US just build a fab? We speak about Moore's Law, the geopolitics of the microchip, and then really so much more as well. And so, as usual, hang around to the end to hear my afterthoughts. And with no further ado, here is the magnificent Chris Miller. Mr. Miller, thank you so much for joining me.
Thanks for having me.
So, while the purpose of our chat today is the thrilling world of semiconductors, I hope that at times your extensive experience with Russia, writing and thinking about it, can shine through as well. And in that vein, I'd like to connect the two from the top, and hopefully it'll also offer a bit of a worldview into sort of who you are and what your interests are. But could you explain why the Soviet Russians were able to create these incredible feats of physics and engineering, the atomic bomb, sending the first guy into space, but they failed to do the exponential shrink and get into the semiconductor game?
Well, this was the puzzle that first brought me into studying the semiconductor industry. I'm by training a historian of Russia's economy. I've written a couple of books on Russian economic history, and one of the things that always made Russia surprising is that it's a relatively poor country compared to most in Europe. And most people wouldn't describe Russia as a technology leader today or 100 years ago, but at a number of important instances, Russia managed to achieve feats of engineering and science. And the classic examples of this are exploding the second atomic bomb in the late 1940s, and then over the course of the 1950s, shooting the first person, and then as well as the first satellite up into space. And so these were accomplishments that showed that the Soviet Union could do technology, at least of a certain type, which then made it puzzling to me that why they weren't able to do microelectronics, semiconductors. Because if you were a country fixated on developing the most advanced military, which the Soviets were, in a life and death competition with the United States over nuclear weapons, which the Soviet Union was. You would think that you'd spend a whole lot of energy building the most advanced guidance systems for your missiles that you could build. And the Soviets tried to do that, but very, very ineffectively, such that by the end of the Cold War in the 1980s, they lagged a decade or so behind the U.S. in terms of the ability to miniaturize computing power on semiconductors. So I wanted to figure out, well, why is that? Why could they make atomic weapons, lots of them, very explosive? Why could they shoot someone into space but not make semiconductors? And it turns out there are a couple of different reasons. One is that for the semiconductor industry, although in the U.S. the first customers for chips were government customers, NASA and the military, by the 1970s, so a decade or two after the first chips began to be marketed, most chips were being bought by the consumer sector, by corporate computers or by calculators or other consumer devices, which meant that there was a vast consumer market that was funding R&D into next generation chips. Whereas the Soviet Union had none of that. There was basically no consumer market. The military was the only customer. So the amount of dollars or rubles, if you will, going into R&D was just that much lower because you didn't have this consumer market subsidizing all the R&D in the Soviet Union. That's one. The second reason, which in my mind makes semiconductors interesting because they're kind of unique, is that the rate of improvement in chips over the past now half century, which we refer to as Moore's Law colloquially, has been so much faster than the rate of improvement in almost any other sector of the economy. And if you look at productivity improvement in manufacturing of cars, that improves by a couple percentage points a year and has fairly steadily for the past half century. Productivity improvements for manufacturing tables and chairs or glasses and dishware, almost anything we produce, a couple percentage points a year is a pretty good rate of productivity improvement. But for chips, we're used to doubling computing capacity every couple of years. And that makes it so much harder to keep up because you've got to be racing ahead at that rate every single year, or you fall not just behind, but very quickly fall orders of magnitude behind. and that's hard to get your head around because most of our life is not characterized by doubling every couple of years. But it makes the chip industry unique and extraordinarily difficult to keep up in. And that's something the Soviets were never able to get their head around. So they could copy really effectively, but they'd copy something, and by the time they'd gotten through the copying, they'd be a couple years behind. So this copying mentality, which was built into the Soviet system, it was so bad that the Soviets, although they used the metric system for most measurements, they had semiconductor machinery that was measured in inches because they were copying American chips that measured in inches. And if you were focused on copying, you could copy very, very effectively, but the time it took you to copy meant you were always behind. And that's the problem the Soviet Union faced.
That's amazing. That last part echoes the current sort of tech trade-off between the US and China largely as well, doesn't it?
That's right. There's some similarities and some differences. The copying question is obviously there. The key difference is that the Chinese have a vast consumer market, which the Soviets never had. And so I think the question is, will that benefit make the Chinese a lot better at building advanced semiconductors than the Soviets ever were?
There's nothing quite as unnatural to the human brain to sort of comprehend as exponential growth, is there? And in this case, it's exponential shrink. You say that you get left behind even if you're just one small order of magnitude off. It's interesting that you explained the difference just literally being the incentives of innovation. The Soviet Union was just incentivized to create the best military output possible, whereas it sounds like the States had the economic incentive, and therefore that was actually the key difference. It wasn't a question of physics capability or anything like that.
And the Soviet Union had a great reputation for excellent theoretical physics. And indeed, when Jack Kilby, who was one of the two inventors of the integrated circuit in the United States, when he was awarded the Nobel Prize, he actually shared the prize with a Soviet physicist who had done some fundamental work on how semiconductors can emit light. So there was great physics expertise in the Soviet Union, and universities like Moscow State University had excellent physicists. That wasn't the problem. But one of the things that's striking about the chip industry is that although there's a lot of science that goes into it in terms of you've got to have a lot of PhDs working in your facilities, it's actually not science that pushes the industry forward. It's engineering, which is something fundamentally different. And no amount of theorizing can make a difference unless you can prototype it, and then unless you can learn to mass produce it. and the prototyping and the mass producing are not really about science. They're informed by your education in electrical engineering or physics or whatever you're educated in if you're working at a chip company, but it's engineering and mass production that are the real things that kind of drive the industry forward.
Hold on to the mass producing thought for later, because I have a good anecdote from when I was speaking to Jos explaining exactly that. That's actually the source that makes ASML so good, not necessarily their innovations in getting the ability to print light smaller and smaller and smaller. It's the ability to do it at scale, consistently, with confidence. Before we move on to that, though, I'd just love to hear you give an explanation for why the Soviet Union had such an extraordinary output of physicists, because it seems like all the incentives were operating against it, yet nonetheless, famously, they were geniuses.
I don't know what the right answer to that question is. I think there are a couple of hypotheses I put forward, but without super high confidence that this is the right answer. I think one is that the Soviet educational system preferenced a strong background in mathematics and in science, so that I think gave people a strong foundation. I think if you were really smart in the Soviet Union and you had a choice, do you apply your intelligence in science or do you apply your intelligence in some sort of practical field? Well, practical fields were kind of not very rewarding in the Soviet Union in many ways. You weren't going to become a millionaire. There was just no way to do that. You could get involved in politics, but politics was a pretty messy business in the Soviet Union. Whereas science was, I think, for a lot of people seen as a sort of way they could use their minds in interesting ways without getting too involved in the practical side of things, which was tragic for the entire country that you had lots of smart people who were only theorizing and not applying. But I think that is why you had so many smart theoretical physicists and other types of scientists in the Soviet Union.
That's actually fascinating. It's your explanation simply just comes down to so many people who would have otherwise applied their brilliance and genius to, say, the pursuit of income. They would have just moved country, like the classic brain drain, like so many fantastic countries do. Instead, they just picked what was the safest career option or something like that.
And if you look at Russia today, where there's no restrictions on emigration, you see so many smart Russians move abroad precisely for that reason. That was impossible in the Soviet Union in most cases.
Fascinating, yeah. Same modern today, the same with the Ukraine. Much of Europe's software development is off the backs of Ukrainians.
Yep. Well, that's a legacy of that educational system, I think.
Well then, before we dive into the geopolitics of it all, because perhaps we should mention, because I suppose I won't have much information to draw upon in the introduction, you're writing a book. When's it due to be published, and then what's the subject going to be?
So the book is titled Chip War, the Struggle for the World's Most Critical Technology, which is going to be a history of how the computer chip has shaped the global economy and shaped international politics and military power. That'll be published in October of this year. And so I'm right now putting the finishing touches on it, sort of as we speak.
I suppose the last year maybe caused you to rewrite a few chapters.
Well, it's funny. I started this in 2019, and when I did, my colleagues said, "You're writing a book about what?" We know what computer chips are, but this sounds very obscure, Chris. And over the past 2 years, I'd say, with A, the geopolitical factors coming to the forefront, and B, the semiconductor shortage, I've ended up getting pretty lucky with the timing in some ways. But I think the other thing about this topic is that although my colleagues asked me 3 years ago, why this topic? In fact, the fact that everyone used to ask that question shows just how little we understood about how dependent we were on transistors. The number of transistors the average person touches a day is in the many, many billions. And we have no idea that we're doing that. There's nothing else that we touch in such great quantity that we are totally ignorant of impacting our daily lives.
If you boil down modernity to first principles, you could make a very strong argument that the most important physical input is the semiconductor, the microchip. And just for the jargon's sake, that's what we're talking about here, right? Transistor, microchip, semiconductor. Yep.
I think that the other way to think about it is if the first part of the 20th century was the age of steel or the age of oil, the kind of industrial commodities, today we're in the age of silicon. There's just no doubt about it. Most of the Most of our work takes place on silicon. Most of our entertainment now involves semiconductors producing entertainment for us. It's just impossible to imagine modern life without it.
Yeah. So clearly the sort of sexy part of this narrative is the geopolitics, TSMC, Taiwan, the supply chain fragility, all the rest. But before we dive into it, really the most impressive part of the story is the complexity that goes into creating these chips and just how remarkable a feat of humanity it is that they're being made. So Jos Benschop made the argument, and he's the VP of technology at ASML, which I suppose I would encourage the audience to do their own research, but ASML is essentially the company that allows microchips, with little debate either side. But he makes the claim that the EUV machine, which creates the most complex microchips, is the most complex machine ever made by humans. It's more complex than the best rocket ship, the best satellite, the best bomb, the best gun. I don't know what other feats of technology there are, but he makes the argument that it is the most complex machine ever made by humans. And that alone needs to be celebrated and spoken about. So talk to me about that. What goes into making a computer chip?
Yeah, I think that's probably right about EUV. But the striking thing about EUV to me is that that's just one step in thousands of steps you need to make a microchip. So at its base, a microchip is a piece of silicon in most cases. There are other materials you can use with lots of transistors carved into that. Now, what's a transistor? It's a circuit that's either on or off. When it's on, it creates a 1. When it's off, it creates a 0. And if you take apart the software on your computer, there's millions and millions of 1s and 0s that it all runs on. And so anything that we're doing on a computer or any sort of electronic device requires lots of 1s and 0s to run, and all those 1s and 0s are expressed by tiny circuits on a piece of silicon going on and off. And when chips were first made in the 1960s, they had a handful of transistors, a dozen or maybe 100 on them. Today, you buy a new iPhone and it has over 10 billion transistors on just its main chip. So the numbers are sort of mind-boggling. If you want to think about the size of a transistor today, the most advanced transistors are smaller than a coronavirus, a fraction the size of a mitochondria. They're so small that it's sort of hard to conceptualize how small they are, but we can see them with certain types of electron microscopes. And when you get an image of a single transistor on an electron microscope today, you not only see the transistor, you see dots that are the individual atoms making it up, because the transistors are so small that they're almost atomic scale in terms of the components thus far. So a handful of nanometers is the length of certain features on transistors. And today's chips either generally compute something, they're logic chips or processor chips, or they remember something, they store 1s and 0s over time, or they convert some sort of real world signal like an image or a sound into 1s and 0s. So those are the three basic categories of chips, and if you buy a new phone or a computer, it'll have all three of those chips in different quantities in them. And so to make one of these, should I go into making one of these right now?
After this comment, that's the best explanation I've actually ever heard of a microchip, because it is just so counterintuitive. I sort of just leave it to a technician. It requires lots of study to sort of understand what that means. But I think that's a terrific explanation. And it also highlights why computing power has gotten so much better, why our computers run faster, why we can run more programs with high definition, etc., etc. It's because literally those 1s and 0s are just being enabled to be computed faster or more efficiently, I would suppose.
That's right, yeah. And when we think of computing power, before I started this research, I thought of computing power as something that sort of emerged from devices or even from software. But basically, computing power is just the number of 1s and 0s you have access to, the number of transistors you have access to. And thankfully, it's doubled every 2 years. So we've got a doubling of computing power every 2 years.
And so that makes a very interesting sort of conundrum, because if we take it for granted, or at least assume that the promise of Moore's law is going to continue, that means whatever the 10 billion transistors we might have access to now is going to square in 48 months. And that's the power of exponential. It gets out of hand very, very quickly. And so I forget off the top of my head, but I think Jos said they'd be down to the atom by 2040 or 2050, which means literally printing light at the accuracy of an atom. Can you go smaller than an atom? It's like a very fascinating question of physics and a challenge for obviously the engineers and scientists involved. But That's an also interesting point to this geopolitical question. We assume that our computing power is just going to get better and better and better and better according to how we've understood it in the past. But there's a very real possibility we hit a wall at 2040. And then what does that do to the progression of technology around us and all the big questions that come from that?
Well, that's right. Moore's law isn't actually a law; it's a prediction that was first predicted by Gordon Moore, the co-founder of Intel, in 1965, and he actually changed the prediction over time. So at first he was getting doubling every year, then he changed it to doubling every 2 years. In the past couple of years, it seems to have slowed a bit further, and yeah, there's no guarantee that even by 2030 it might not slow down. I think what we can say is that there are certainly physical limits to how far we can go down the current pathway of shrinking transistors. At some point, we're going to get to one atom, and you can't get to half of an atom, at least in any sort of way that we understand today. But we can also say that right now, there is more money than ever and more smart minds than ever trying to figure out new ways to deal with these issues. And there's not just one process underway. It's not just shrinking transistors. There are multiple different ways you can shrink them. You can stack them three-dimensionally. You can organize them in different ways. You can use new materials. So there's lots of different ways where we're going to make incremental improvements. And when you add up all those incremental improvements in the past, that's what's gotten you the exponential increase in Moore's law. So it's not as though we're relying just on one discovery. We're relying on every year substantial improvements across the supply chain, which when you add them all up, they've delivered Moore's law in the past. And because of that, I think I'm more confident than I'd otherwise be that we're going to keep getting improvements. At what rate, hard to say, but the thesis that progress just grinds to a halt seems implausible given all of the resources we've got in terms of brain power, in terms of finances to find the discoveries that we're going to need for the next generation.
So take us into then what goes into making these chips.
So today, the challenge of making a chip is making transistors that are so small. It's not like you can take your standard machine tools and dig out a hole in the silicon and fill it in with the materials you need. Transistors are made by etching holes into silicon and then depositing certain metals or other material into the holes in the right amounts. That's a sort of
incomprehensible scales of smallness. Yeah, because you explain it like that, I feel like, oh, that's a microscopic machine making little indents. Like, no, it's beyond our comprehension of small scale. Yeah.
That's right. And if you think of a silicon wafer, which is most wafers are 12 inches today, are the most modern wafers. They've got, it depends on the size of the chip, but call it a couple dozen chips on them, and each of those chips will have 1 billion or 2 billion or 5 billion transistors. So on a wafer, you're talking many billions of transistors, and you process them all, generally speaking, simultaneously. So when you do a process step, it's got to have an effect on all of the transistors at the same time. And your margin for error is limited. You can't have 5% or 10% or 20% of the transistors not operate the right way. And because you've got transistors that are a couple nanometers or a couple dozen nanometers in size, you don't have much scope for error. So you've got to have these ultra perfect manufacturing processes that can produce transistors by the tens and hundreds of billions almost flawlessly. And that's understandably really hard to do, which is why there's just a couple of companies that know how to make the machines to do it, that have the specialized materials and ultra pure gases, and then that know how to actually put all these different pieces together, which is what the actual chip making companies do in their fabs. And because this is so hard, it's required this vast supply chain to actually make it possible. If it were easier, you could have more simple supply chains. But when I listen to people say, well, let's onshore the semiconductor supply chain to country X or country Y, I say, do you have any idea what you're talking about and how hard this is to do? Who do you know that can produce 10 billion transistors with 99% accuracy on a single silicon wafer? Well, there's one company in the world that can do step Y or step Z, and that's the challenge today, is doing it with perfect accuracy.
So go a bit further into it. Really romanticize the ingenious complexity of the EUV machine. Could you try and take us into what it takes to do that at scale consistently. I'll just say one quick anecdote. Jos explained what 10 nanometers was to me by saying, look at your fingernail for 3 seconds, and that's 10 nanometers. So printing to that accuracy, like you said, with very low margins of error, hour on hour on hour, every day, without fail. It's up to technicians to understand how complex that is, but please, if you could explain that.
Okay, so silicon wafer, we need the most pure silicon you can imagine to produce a silicon wafer. Then,
Which is sand.
Which is sand at its core. That's right. Very, very expensive, complicated sand. So you take this silicon wafer, and then there's a series of steps of lithography. And the way you do lithography is you cover it with a chemical, the wafer with a chemical that reacts to light, or to ultraviolet light in this case. And then you shine a pattern of light onto the wafer. And you need this pattern of light because it will react with the chemicals in the exact pattern that you shine on it, and then we'll let you carve out that pattern onto the chip. So to use extreme ultraviolet light, which is the type of light that we now use for the most advanced chips, is complex because it's very, very hard to produce extreme ultraviolet light in the power that we need to actually react with the chemical and on the wafer. And so to do this requires some of the most complicated machinery on Earth. It requires the flattest mirror humans have ever made. It requires these extraordinary systems that hold mirrors stable, because any tiny movement in the mirror will reflect the light in a different way. And it requires an ultra-powerful laser to start. And so the laser is made by a company called Tufts in Germany, which then shoots a laser and pulverizes a tiny ball of tin to several 100,000 degrees Fahrenheit. It does this tens of thousands of times a second. The numbers are just kind of mind-boggling. EUV is emitted. This extreme ultraviolet light is emitted. It's collected by mirrors, and the mirrors themselves are complicated because extreme ultraviolet light is sort of like an X-ray. It goes through most materials, like an X-ray does. It'll go through your body. So you need specialized mirrors to actually reflect this type of light. And so the mirrors themselves are made of layers of 2 different types of materials that are themselves a couple of atoms thick. So every piece of this machine is sort of an engineering marvel. Anyway, you collect the light, you shine it, or you reflect it off of the pattern you want, eventually reflected on the wafer, and then it's shined onto the wafer. And then you've got the reaction once the light hits the wafer with the chemicals you put down. Then you can and where the light hits the chemicals, the chemicals will often will react one way. Where the light doesn't hit, the chemicals will be in their initial state, and then you can use other chemicals to wash away the chemicals that weren't struck by light, and you'll be left with a pattern on the wafer, and this pattern will be in the shape of certain of the transistors that you want. Then there's additional steps. You then etch holes into the wafer by using additional types of plasmas that you expose the wafer to, and the plasma will react with the silicon, create the holes you need in the silicon, and then you can wash this all away with different chemicals. And this process is repeated time after time. So there's often 1,000 or 2,000 steps in in the creation of an individual wafer.
I love the anecdote that you gave in the Bloomberg interview about how amazing, we're talking about ASML specifically here, but I suppose the same anecdote could be made for a lot of the sort of supreme chip manufacturers. But just how sophisticated the supply chain is. And you mentioned there that piece of glass, which is in itself a remarkable feat of engineering, the flattest material ever created by human beings. I just want to again emphasize its exponential shrink, its types of scale and accuracy that is, it boggles the human mind. It's so impossible to appreciate. That little anecdote you gave about the tin, again, I encourage anyone listening to go to the ASML website and try and look at their sort of animation of how this works, because it's impossible to appreciate until you are sort of just smacked in the face with it. Wait a minute, you have 10,000 drops of tin, actual tin, going across a surface that a laser shoots into at perfect accuracy to then create all of these reactions of light that then prints onto a wafer that, whilst may look thin, has this stabilizing mechanism added underneath. The temperature in the machine has to be kept to within 1,000th of 1 degree because any margin of error is going to fuck things up. It's heavy machinery moving, yet somehow you've stabilized everything. It's crazy. It's just unbelievable.
But I think the craziest thing is it would be one thing to have this happen once or once a week or once a month, but it's operating constantly, 24 hours a day, flawlessly or close to flawlessly. And that, I think, is the really striking feature. And that's the difference between science and engineering, in my view, because scientists can do a cool experiment once or maybe a dozen times and prove the result what they want. But that's not what this is. This is about producing something that is going to be reliable enough that a company will be willing to spend $150 million on it and put it in their facility and bet their $20 billion fab on it. And so it's got to work almost all the time.
So Jos says it's the most complex machine ever, but I think he's quite biased in that opinion since he was one of its creators. What do you think? Is the EUV machine the most complex machine ever created by humans?
It's certainly up there. If you look at just one of the key components, so the laser that goes in the EUV machine, the laser alone has 457,000 component parts, just for the laser.
Did you say 457,000?
Yeah. So the numbers are wild. And these aren't just sort of off-the-shelf parts. Many of the parts inside the laser are themselves engineering challenges. So it's sort of an onion in terms of you peel it and you find another engineering challenge below it. I think if you look at a 747 airliner, you'll find that I believe the number is 6 million components in one of those. So the number of other things you can compare EUV to is very small. Maybe you compare it to a 747, which also operate basically flawlessly, flying around the world. But that must be just about it. I struggle to think of anything else that's close. And if you look at the price tag of an EUV machine, $150 million plus or minus, that gives you a sense of just how much complexity we're talking about, because there's not many things that cost that much for a manufactured good that you can buy off the shelf.
Fascinatingly enough as well, I think you also said this in the Bloomberg interview, they only sell a few hundred or thousand machines per year, right?
Right.
Yeah, I think it was a couple hundred last year, and obviously they're trying to ramp up to meet demand. But the precision you need, it's difficult to do mass production and precision like that simultaneously. I think the other factor is that if I were to give you a UV machine, you or I wouldn't have any clue what to do with it. There's not an on button you press and started producing. You need to train your personnel and have your machine optimized to your specific factory. So that alone is an education process that companies need to sort it out. So it's not just can you produce enough machines, it's also can you train enough people to know how to use them effectively.
Yeah, if we take TSMC, I always get the acronym wrong, but the fab in Taiwan, ASML has full-time employees positioned there. They chartered a private flight with extremely complex transporting mechanisms to get it over there. The installation is itself a multi-million-dollar process, the type of clean rooms that's required. The whole thing is, truly amazing, which does lead us into the geopolitics, I think, quite neatly. But before we go there, can you distinguish between the different types of chips? Because what we've just been speaking about is the highest end, the MacBook, the iPhone, etc. But not all chips are created equal. So could you give us a lay of the land, chips in total?
So generally speaking, the way you talk about how advanced a chip is by referring to the node that it's produced at, and a node is referred to as a number of nanometers. So today the most advanced are 5 nanometer, and next year it'll be 3 nanometers that TSMC is producing. And in the past, the node referred to a specific length on the transistor. Today, transistors are actually 3D in their structure, so the node is just sort of a marketing name at this point. But you know how advanced of a chip is based on the node level. The smaller the node, the more advanced that it is. And so the most advanced chips are produced on the smaller nodes because you get more transistors per square inch and more computing power as a result. So for your phone, for your computer, also for your data center, if you're running a lot of AI workloads, you want the most advanced chip you can get. But For a lot of things, you don't necessarily need a whole lot of computing power. In your car, for example, there's dozens of chips that are managing the window going up and down or fuel injection into your engine. And that's a relatively straightforward process where computing power isn't that intensive. So there's plenty of demand today, not only for the most advanced, which we obviously need for the devices that I mentioned, but also for the less advanced, because we're still using more and more of these less advanced chips on a regular basis as well. And especially as things like cars and industry get more and more computerized, require more computing power, they're going to be drawing more heavily on these lagging edge nodes, as they're referred to in the industry.
How about some numbers? How many chips go where?
So we can say about dollar value pretty straightforwardly. About a quarter of the dollar value of chips produced a year go into phones. So phones are extraordinarily chip intensive because there's not only the main processor that's going to run your operating system, there's a chip that manages the camera, one that manages the Bluetooth, the cell phone connection, the battery. There's a memory chip. You'll often find a dozen or even up to 20 chips in a typical phone. Computers are slightly less important than phones in terms of the number of chips that go there. Data centers are growing very rapidly in terms of their demand as we have big cloud computing companies grow out their data centers. A data center is basically a massive building full of chips. That's what a data center is. So there's these massive facilities stocked full of the most advanced chips that we can produce. And then when you look at other markets like autos, aviation, they're really quite small in terms of dollar value. 5 or 10 percentage points in total of chips by dollar value will go into a car or an industrial use, for example. But for the auto sector in particular, where we've seen the most chip shortages of the past year, the challenge is that if you've got a car, you need every single one of those chips in the car to be present. Even if you're only missing a 99-cent chip, your car might not work. And so because cars are big, complicated pieces of machinery that have a bunch of different chips in them, over the last year, 18 months, we've seen a lot of car factories halted because they couldn't get a $2 chip that managed the fuel injection into the engine. And for chip makers in Taiwan and elsewhere, car companies haven't been that important because they pay relatively low dollar for their chips, a couple dollars versus a couple $100 for an advanced data center chip. And so that's why we've seen the most news stories about auto chip shortages, even though for chip makers, auto's a second-tier market in most cases.
Interesting. I was under the impression that TSMC only produced the highest end of chips, but do they have a range? They're producing them all.
They do, yeah. And if you think of the business model for a chip maker, you build a new set of manufacturing facilities every 2 years or so for each new node that you produce, but your older factories are still completely functional. And so it's actually the lagging edge ones that are the most profitable because you've already paid down the cost of your equipment, which is the expensive part, and it's just pure profit.
Well, that brings us then naturally to where they are produced. So we've hinted at Taiwan. That's the granddad. That's the dragon of the industry. But take us into where they are geographically, and also if you could also comment on how sophisticated they are and maybe how big they are.
So to do this, I think we want to distinguish not only between how advanced the chips are, but also types of chips. So if you look at processor chips or logic chips, which would go into your phone, your computer, your data center, distinguish those from memory chips, which also go into phones, computers, and data centers, but do different things. Processors process data, memory chips remember data. Memory chips are disproportionately produced in Korea. There's two Korean firms, Samsung and SK Hynix, that are the two biggest producers of memory chips. The rest of the memory chip output is produced a bit in Japan, a bit in Singapore, a bit in the United States, and a bit in China by Korean companies. But Korea is sort of the center of the memory chip world, if you will. For logic chips, it's different. Most logic chips are produced by foundries, which is a type of company that only does manufacturing. So you'll design your chip, you'll bring it to the foundry will manufacture it for you. There's one big exception to that, and that's Intel, the US company that makes chips for computers and for data centers, and Intel produces most of its own chips in-house. So they'll both design and manufacture their own chips. Intel's production is mostly in the US and Europe and Israel. But for chips that are designed by different companies and then produced in a foundry, most of the world's foundry capacity is in East Asia and especially in Taiwan. Taiwan has over half of the world's foundry market.
No way.
And TSMC is the giant right there. So not only does TSMC produce the most advanced chips in the logic segment, but they've also got by far the most capacity of anyone else in the market. And so if you're a company like AMD, Qualcomm, NVIDIA, big chip designers in the US, you've basically got no choice but to rely on TSMC for at least a big chunk of your production because no one else has the capacity and the technological capability to actually do it.
Wow, and that just perfectly explains the geopolitical mess of it all. What about China? Because there's lots of chat about, them, I suppose, monopolizing or cannibalizing. I don't know what the right term would be, but there's a lot of chat about them taking a lot of that demand and producing it there themselves because obviously they can afford it, I suppose. Like the economics doesn't have to be extremely supply-demand sensitive. They're happy to take a loss if it means they get some sort of geopolitical power as a trade-off.
So right now, China actually plays a pretty small role in the fabrication of chips and in the chip supply chain as a whole, but it's changing rapidly. And so it's easy to see how in a decade China could be a much bigger player. If you look at chip fabrication in China, what you'll find is that there's no Chinese firm that's anywhere close to TSMC in terms of technology or in terms of capacity at more advanced nodes. So China produces a fair number of low technology, older chips, but not much that's in the cutting edge space. And China's also quite... Yes, and this has been a kind of long-term focus of the Chinese government to change this, but it's really hard to change because even if you catch up to where TSMC was 4 years ago, TSMC is 4 years ahead of that point right now. And so the best Chinese company in this regard is a company called SMIC based in Shanghai, which has made some pretty good efforts, but is still pretty decisively behind where TSMC or other firms would be. Now, this is going to begin to change, at least in terms of capacity, because China's government is pouring money into subsidizing the build-out of capacity of chip makers in China. But capacity is different from advanced production. And so I think it's undeniable that China will produce more chips in 10 years than it does today. I think it's still very unclear whether China will produce relatively more advanced chips than it does today. Certainly it will advance, but I think Taiwan might advance faster than China does. And so right now we have a situation where China spends more money importing chips than it does oil. China's the world's largest chip importer of any country. The numbers are mind-boggling. That's such a good stat. Yeah, it's in the hundreds of billions of dollars a year China spends importing semiconductors from South Korea, from Taiwan, from Malaysia, from other countries in Southeast Asia. And that looks unlikely to change in the short term because even if China's completely successful in building out its own capability to produce a lot of low-tech chips, it's still going to rely on Taiwan for the most advanced chips.
Okay, so if chips are so important that they're outstripping the demand, if they're outstripping the cost of energy, can you please help me understand why then it's not possible for, say, the US, the biggest country in the biggest economy in the world, China, etc., to onshore this type of manufacturing? How can we explain why TSMC is so far ahead and why no one else can catch up?
Well, I think it's just largely a cost of money, which is to say that TSMC has plans to spend $100 billion building new chip facilities over the next couple of years, and I believe the latest number is $40 billion this year. So if you wanted to replicate what TSMC's got, you need to spend that amount of money for years on end just to get to where they are today, and then you need to outspend them once you've actually caught up to them. So it's just very, very difficult to do. Now, some countries have roughly comparable capability. So if you look at the US, Intel is behind TSMC, but only a little bit behind. So Intel could plausibly in 5 years catch up, hard to say. Samsung in South Korea could plausibly catch up to TSMC or even overtake it, hard to say. But if you're starting from scratch, I mean, I don't think I would bet against TSMC, but you could imagine TSMC slipping up and somebody else jumping ahead. But it's not going to be someone you've never heard of, because if you're starting from scratch, you've got to build up an extraordinary amount of knowledge. It's capital intensive, and it's just something you can't invent overnight. TSMC has now had almost 35 years building up its expertise, and one of the secrets of TSMC in the early days is that TSMC was founded by a bunch of Texas Instruments executives. And Morris Chang, the founder of TSMC, spent his career in Texas working at Texas Instruments, where he actually kind of built the chip industry in Texas in many ways before moving to Taiwan.
What a legend.
It's an extraordinary story. And so you've got this refugee from communist China, enrolls at Harvard, the only Chinese person in his class, wants to study Shakespeare, but it decides that there's no career prospects for him in English literature, so transfers to engineering, and then is present at Texas Instruments basically at the time when they're inventing the first integrated circuit, the first chip, builds up the industry in Texas, and then no one else in the world has a better understanding of the industry than Morris Chang. When he moves to Taiwan in 1985, it's not like he's starting from scratch. This is the expert among everyone in the world in doing so. And so if Taiwan had hired anyone else, they wouldn't have made nearly as much progress than they did thanks to hiring Morris Chang.
What a wonderful story of serendipity. You can't predict a future of infinite possibilities based off a finite experience of the past. It's those sort of things are so amazing. Help me understand why it's so expensive, because you just said up to $40 billion a year, and potentially if someone wanted to enter the industry, they'd have to catch up. So drop a ball, so ballpark 200 billion plus potentially, I'm not sure. The EUV machine, I think, is like 150 million euros. So just for one of them. Okay, so is this... Please explain why it's so expensive, just to help me understand where all these costs are coming from, because that's a big escalation there.
So if you build a modern fab, you got to put modern equipment in it, which means not just one EUV machine, but multiple. So TSMC will have a handful of EUV tools in each of its fabs, which will cost, call it $20 billion each. But it's not just an EUV machine. You need deposition machines, you need etching machines, you need metrology machines that will let you identify individual errors on a silicon wafer. And when you add up the cost of all this tooling, it's enormously expensive, several $1 billion just for the fab. The buildings themselves that you produce semiconductors in are also quite complicated. You need the purest air you can imagine, because a single particle of dust can cause all sorts of difficulties. You need the ultimate in earthquake proofing, because just as the machinery on the EUV machine has to be held totally still, the rest of the fab has to be totally still as well. So, these are arguably the most expensive factories ever produced. And each time TSMC builds a new facility, it's again the most expensive factory ever produced, because it's more expensive than the previous one, because there's so much complicated tooling in them, and because the environment has to be so pristine to actually make chips effectively.
In your estimation, as someone who has done the deepest dive, potentially of any journalist or author in history of this subject, how possible is it that within 5 to 10 years we see a shift away from TSMC being the dominant producer and a strong presence in the United States, potentially Europe, potentially China? How do you see it playing out?
I think it's very possible that TSMC in 10 years is not considered the manufacturing leader. Over the past decade, we've seen companies slip up. Intel used to be the company that everyone wanted to beat. Intel was founded by the guy who invented Moore's Law. It still is enormously profitable, and yet it slipped up over the past 5 years. So there's no reason why TSMC couldn't do the same. If I had to bet, I'd bet they'd keep doing a pretty good job at executing, but it's certainly possible. But if anyone's going to catch up to TSMC, it's going to be a company that we know of today, because of this prior investment you got to do. So I think Samsung and Intel are the only two potential competitors. If you look in Europe, there's just no one in Europe that's done the investment in this type of chip making to get anywhere close. And China would love to be close, but right now it seems extraordinarily difficult to imagine how China would be able to get close or to be allowed to buy the machinery that you need. Because right now, because of Dutch government regulations and U.S. government pressure, you're not allowed to ship a UV machine to China, for example.
No, really, the Dutch dropping the hammer. Good on them. I mean, good on them. I'm projecting too much of my politics into this, but I suppose it's worthwhile having sort of sanctions on some things like that. So, okay, that introduces perfectly the sort of geopolitics of it all. And the story that you just told is one of extraordinary fragility on several manufacturers in East Asia, which is far away from the biggest economy in the world, the United States, the biggest emerging economy, the continent of Africa. How can we explain this fragility? Taiwan is not even its own sovereign country, and South Korea has enemies to its north and to its west, and I suppose Japan could be an ally of sorts, but that's two very precariously placed locations for what is, you could make a very strong argument for, the most important component to modernity.
I think you're right, and if we were redoing history, I think we would not accept a situation where we had so much concentration of risk in this part of the world. I think it's inevitable we get concentration because the industry requires such capital intensivity. There's been a trend towards monopolization or creating oligopolies in certain types of parts of the supply chain. We see it in lithography. There's one company that makes EV tools, and there won't be another one. But that's not the only part of the industry. There's numerous parts of the supply chain where there are one or maybe a handful of firms that basically control their sliver of the supply chain. And I think this trend towards concentration in the chip industry is, to a certain extent, inevitable. But why did this end up being concentrated so much in Asia? Well, to understand that, you got to look back to the earliest days of the chip industry. So when Bob Noyce and Gordon Moore founded Fairchild Semiconductor, which is kind of thought of as the first startup in Silicon Valley. They founded it in the late 1950s. They were immediately faced with the problem of how do you get enough workers to assemble chips. So once you've fabricated a chip, you need to have someone stick the wires on it that then go from the chip to the rest of the device, for example, and that was always a laborious process. And so they hired workers from California, but they quickly discovered that they could pay people 1/10 of those wages in Hong Kong. And so from its earliest days, early 1960s, Fairchild had opened a offshoring facility in Hong Kong. And from that point onwards, every chip company in the United States had offshored production facilities. And when you started having chip firms in Europe and Japan grow after that, they too started offshoring to East Asia. And the cheapest labor in the most organized fashion was Hong Kong, Singapore, Korea, Taiwan, Malaysia, which is why you've got this focus on East Asian supply chains today.
Talk to me a little bit more about the geopolitics, and forgive me if I'm belaboring the point, beleaguering, not sure what the word is, but if Taiwan was without TSMC, how much would the US really care about Taiwan?
Well, I think if you look at the U.S.-Taiwan relationship, what you'll find is that the U.S. cared the most about Taiwan and was willing to spend the most defending Taiwan in the 1950s, when Taiwan was the least important to everyone. And in the 1950s, we almost went to nuclear war with China over Taiwan during the first and second Taiwan Straits crisis.
No idea.
Yeah, in the late 50s. And at that time, Taiwan was an impoverished island that was totally irrelevant to the world.
Yeah, they'd just been... they just had the Chinese nationalists come in and sort of run it over, right? Yeah,
That's right. So I think the question of would the U.S. care about Taiwan still, and the answer is yes. But I think there's a different question that I'd ask, which is what would happen if things go wrong in the Taiwan Straits and you get some sort of military escalation between China and Taiwan, or maybe something that brings in the wider region. And there I think that in addition to being a disastrous war, which it could well be, and I worry about, you'd also have profoundly tumultuous effects on the rest of the global economy, because Taiwan produces around a third of the new computing power we rely on every year. And if that were to disappear, it would take over a decade to rebuild. And in the interim, we would have a third less ones and zeros on which to run every piece of software we want to run. So smartphones, computers, the telecom infrastructure, autos, airplanes, dishwashers. It'd be hard to buy almost anything the first year after. And I worry a lot that we're not prepared for that.
Talk to me about what you think is the likelihood or possibility of genuine conflict that will disrupt the global supply chain more than it already has. I'm not saying all-out war, but in the realm of possibilities.
Well, I think it's frighteningly possible. It's easy to assume that because the situation in Taiwan has been relatively stable over the past 2 decades, that it will stay stable. But it was as recent as the 1990s that the Chinese shot missiles over Taiwan and the U.S. sailed an aircraft carrier through the Taiwan Straits to force the Chinese to stand down. And it was only a couple decades ago that the Chinese were still regularly shelling islands that the Taiwanese control in the Taiwan Straits. So I think we should be concerned. I look at Eastern Europe today and say, many people told me that we were done with warfare in Eastern Europe, and now I guess I look at the risk that we're about to enter a new one. And I think the same thing could well be true in Taiwan. And it doesn't have to even be the result of a deliberate escalation. It could be that one side decides to escalate, but it could also be that there's an accident happening. 2 planes collide in the sky or 2 ships at sea, and no one wants to admit they were at fault or back down. Any of those scenarios, I think, could lead to something really dangerous in political terms, but also in economic terms.
And so does that explain the last 12 months, the sort of geopolitical flare-up and attention to chips, the identification of just how fragile the global supply chain is because the majority of the chips comes from this disputed island in the South China Sea?
I think it's partly that. There's another part of it as well, which is that the U.S. and a lot of other countries, but I think the U.S. has been particularly focused on this, is coming to realize that the next generation of economically crucial technologies and also militarily crucial technologies will depend on computing power. And so making sure that you've got an advantage in your ability to produce computing power is going to be important, not simply so you can have the best metaverse, but so you can have the best military too.
Wow.
And so the U.S. has historically tried to keep a couple generations ahead of China in semiconductor technology. And that was easy to do in the 1960s and 70s and 80s. That's getting harder to do now, which is why you've seen the U.S. try to impose more restrictions on the transfer of technology to China to make sure the U.S. has the technology it needs to keep its military edge.
That paints significant incentive for China to occupy Taiwan.
Well, the trick for China is that although it would love to own Taiwan, the prospect of conquering Taiwan would be difficult to do with the semiconductor facilities intact. Because if you start thinking about explosions occurring around an EUV machine, it wouldn't take much to knock some of the ultra precise instruments out. So I struggle to imagine a scenario where you have fighting and TSMC's fabs remain intact. And it would only take 1 or 2 disgruntled engineers in Taiwan to sabotage the entire situation if in fact the Chinese took over. So I don't worry as much about the Chinese saying we're going to invade to take over the fabs. I worry more about the Chinese saying we're going to invade anyway because we want to control Taiwan, and in the process knocking out not only Taiwan but also this kind of crucial node for the global economy.
There's almost like there's another sort of idea of mutually assured destruction. If the engineer does decide to just sabotage things, so I wonder, could you view TSMC as some sort of military advantage? If so, it's like can be considered a weapon. If so, it's like a heroic act to say, well, I'm not going to let China get their hands on this, nor the US. I don't know.
Yeah, well, and it's clear that the US wouldn't put it this way, but the US is trying to sort of weaponize, if you will, TSMC more now than ever in the past. It's been trying to cut off a number of Chinese firms from being able to produce chips at TSMC on the grounds that certain Chinese firms have produced chips for TSMC and then put them into Chinese military equipment. And in the past, the U.S. kind of turned a blind eye to that type of thing. Now they're being much more tough and saying, we demand that TSMC produce chips for U.S. military equipment, but we don't want that to happen with Chinese military gear.
To return to something you just said before, if say TSMC was disrupted or ruined completely, it might stifle the progress. It would just be this unbelievably disruptive event on the global supply chain, which really highlights another point, which is that how important computing power is to the ongoing innovation of modernity and our technologies, and just how much we really, really, really rely on it. Could you just emphasize that point for us?
Yeah, I think if you start to think about the number of devices you have that don't have semiconductors, it's there's very few devices that you rely on a daily basis that don't have semiconductors, and that's only going to increase because as communications get better, as it becomes possible to send more data through the airspace with 5G telecom technologies, the incentive to use more computing power in more types of devices will only increase. And so we talk about the Internet of Things, phrases like that, but that's really just beginning right now. And I think if you look forward a decade, you're going to see more and more devices that are plugged into each other in terms of their ability to transfer data to one another, which means that they're going to have multiple types of chips in them, some to process the data, some to remember the data, some to transmit the data. And as we get more and more computing power in the same amount of space, thanks to Moore's law, it'll be possible to make even simple devices smarter, because right now intelligence is complicated and it's expensive, but in 2 years we're going to have twice the processing power thanks to Moore's law, and 2 years after that twice the same amount again. And so we're going to have smarter and smarter devices across the scope of devices we're looking at. So I think we've only begun to think about what will autos look like in 10 years, for example. Today we think of autos as something that will drive us around town. But if you look at the semiconductor content going into new cars, and especially the more advanced new cars like Teslas, the number of transistors in a Tesla is extraordinary. And I think we're only beginning to understand what those will be used for going forward.
Take us into the future then. 4 years, we've doubled computing power twice. How do you see chips affecting technology around us in a very tangible example?
Tangible example. I mean, in some ways, we're so used to this process happening, we take it for granted. We take it for granted that everything will be better in a couple of years' time. Our connections will be better. Our phones will have higher resolution cameras on them. The entire thing. I think the key thing that we're just beginning to roll out is the ability to have artificial intelligence present not just in vast data centers for things that companies make priority projects, but rather for all types of devices. So we're going to have devices that are more focused on looking at what we do, learning from it, and operating accordingly. And when we think of artificial intelligence, I think most of us think about algorithms. And then after algorithms, you think about data. But in fact, what makes artificial intelligence possible to roll out at scale is computing power. Because the reality is we've got tons of data, more data than we know what to do with. And algorithms are something one can write, but the real limiting factor is, can you get enough processing power on your device to run whatever artificial intelligence application you want to run? And we're right now getting to the point where the answer to the question is increasingly yes, that we've got the processing power, so we can not only make our most advanced data centers smart and have them churn through lots of data, but we can also make our dishwashers smart and our cars smart and our cell phones smarter than they are, because we're going to have the transistor budget, so to speak, the number of ones and zeros you need to actually do that.
That's it. The last one was exactly the one that I was thinking about. Smart iPhone. The amount of interaction you have with that technology on a day-to-day basis, if it didn't just rely on algorithms and say your Gmail, your Google account learning from its behavior and interaction, but the entire interaction with the phone and it improving over time, which is entirely possible. It's simply a matter of computing power. We have the technology to actually do that. Kind of, the software is going to be able to develop in lockstep with the increase in computing power. We can't imagine. That's actually kind of the exciting part of it. So much of the applications exist in the unknown. It's the fourth order consequence that was totally unpredictable, which ends up being the future of humanity. So that's fascinating, incredibly exciting. I was just struck, Chris, while you were answering that question, how much of an authority you are in this subject. You haven't stuttered once, no ums, no thinking. It's all top of head. This is really amazing. So thank you for that. I want to draw your attention towards a company called Planet. You just mentioned the unknown potential of data. This is maybe me just projecting too much what my interests are at the minute, but this company, Planet, are you familiar with them? Yeah, okay. So for the audience, biggest satellite company in the world. They have the most in orbit. They're imaging the planet daily, which basically means you're going to have a historical data set of how the image of the surface of the Earth is changing over time. It's amazing the type of applications we can do with that. And this is such a tangible example that is enabled by the processing power. And 10 years ago, no one thought that, well, people might have seen that as a potential, but it wasn't possible. I see Planet as an archetypal example of what power processing can enable, and for the betterment of humanity and the future as well, because obviously there's the weaponized component of it, but there's also just amazing liberties that technology is going to afford us.
I think that's right, and when you are able to marry the data, the new data, whether it's image data, word data, whatever data it is, with the processing power, that's where you get the real extraordinary advances.
One more in geopolitics, and then just one more in the geopolitics. Jos disagreed with me when I brought this up with him, but in another interview I had with a man called Vince Beiser, who wrote a book about sand and that natural resource and its shortage in the planet and its importance in cement and so many other products. Silicon that they're using to print these microchips on is of the highest grade. And so far there's actually just one place they get it from, which is in the United States. Correct me if I'm wrong there, but it's this one small mine. It strikes me that there is a very real potential of a silicon shortage here. Did you come across any of this in your research?
That's interesting. I haven't. Whenever I hear about shortages in semiconductors, but in any industry, shortages I think are always just a question of at what price, because there's no doubt that if you have a shortage of a certain type of purified silicon, if you spend another couple of years and develop some new technologies, you can purify some more silicon to get the amount that you need. I think there's no deficit of silicon in aggregate across the world, whether we've got the supplies we need today of the purest types, I don't know.
Right. It was just in conjunction with the same silicon is used for solar panels, and given the sort of green revolution, there's millions and millions of solar powers being created, right? And it posed a question, but it seems like it also didn't raise a flag for you as well. So it might just be something overinflated.
Yeah, I haven't heard people worry about that, but that might mean that we ought to be worrying about it. I'm not sure.
Maybe. All right. Well, look, I think that was fascinating, and you've answered all the questions I prepared. I wonder if there was anything that we missed in the geopolitics of semiconductors, or some great anecdote that you really wanted to talk about that was something memorable from your book, for example.
I think you've covered all the key questions from my perspective, so nothing that stands out. I think we covered a lot of ground.
Well then, I will leave you with the final questions that I try to ask as many guests as possible. The first being, talk to me about a moment when you look back on it, you just can't believe that you were so lucky to be a part of it. And I will give more context if you want.
Well, in the course of this research, when I was in the early stages, I was trying to understand how the process of lithography that ASML does today, where it came from. And there's a guy named J. Lathrop who was the holder of the first patent for semiconductor lithography in the U.S., who patented his this process in 1958, I believe. And I presume that he was long deceased, but I Googled the name and found his LinkedIn profile, if you can believe it. And 2 years ago, I sent a message on LinkedIn, and we got in a fairly long conversation about his work. He's 90-something today, but still kind of very sharp and happy to discuss the origins of lithography. So I've had a number of incredible interactions like that with people who were present at the creation of the industry and knew some of the great figures who founded it, which was the most fun part of this research.
That's amazing. How does he think about where it's gone from what he would have conceived in the 50s?
He's the most modest man I've ever corresponded with. In my view, he's got as much right to claim that he created the chip industry as anyone, since this process is so fundamental. But he has no sort of grandiose view of his own role, and I think was just appreciative to be able to take part as a physicist and engineer, and in some ways sort of a paragon of what you think an engineer and a scientist ought to be. I came away with the utmost of respect for him.
When you look into the future, we've spoken quite a lot about the chips specifically, though this doesn't have to be chip specific. And also I sense you have a deep admiration and love for Russia. But this is a question I like to ask every guest. What is a country that you're most bullish on looking into the future?
Well, I might have a counterintuitive answer, but I actually come away thinking I'm most bullish on the United States right now.
Nothing counterintuitive about that.
Well, sitting in the U.S., that might seem like a counterintuitive answer. I guess I'm struck by having studied the history of Silicon Valley, and not only Silicon Valley, but also the rest of the U.S. tech infrastructure, which extends to Texas and to the Boston area and to upstate New York. Just how many times it's succeeded in reinventing itself. And even when it seems like it's on the brink of failure, it's managed to reinvent itself again in ways that surprise almost everyone. And so I guess if I not only from the chip industry, but more broadly, when I look at countries' ability to sort out problems and find ways of reinventing themselves, it seems like the U.S. does have that track record. And the booms and busts in Silicon Valley, for example, are extraordinary, both in the booms and on the busts. But it does seem like there's always a boom after each bust, and that's something that there's a lot to be learned from.
I'm surprised you say it's counterintuitive, because that might just be a consequence of you absorbing the daily news cycle. If you step back, I mean, I think it's the easiest bullish case to make, to be honest. Do you listen much or read much Peter Zeihan?
I'm familiar. I haven't read in depth.
Well, it's, he's got I subscribe heavily to his worldview. It's a lot of it is sort of prediction, and prediction is largely folly, I would say, at least, based off what I said earlier in terms of predicting the future of infinite possibilities based on finding experience in the past. But he makes the case for US coming out on top in this sort of Thucydidean argument between the US and China. And it's pretty compelling once you take into account just a few sort of baseline factors, which you're very familiar with, which my audience has probably heard ad nauseum, so I don't need to say again. But I would recommend it to you to look further if you're interested. Finally, Chris, my favorite question. If you could listen to a conversation, a podcast, between any two people of history, dead or alive, no language barrier, who do you want to listen to?
Well, that's a great question. I would go back to the ancients. I think I'd like to listen to a podcast between Socrates and Plato to see how the ancient Greeks did podcasting and to understand the core of their philosophy, or someone else from a period so far ago it's hard to understand how they actually thought. We've only got fragments of the great ancient philosophers of their writings, and I think listening to them in conversation would be revelatory in many ways. Couldn't
agree more. Well, Chris, I found that absolutely fascinating. Thank you so much for giving me the time.
Well, thanks for the invitation.
Well, cheers, Chris. I hope you guys realized that comment I made about halfway through. Chris didn't stutter, trip, or commit any other auditory mistakes once. It was really an amazing thing to see live and then in editing after. His book is not available yet, but follow his website and his Twitter, both of which are in the podcast description. And just so you don't miss it when it comes out, because I imagine when this book is released, Chris will be hot property on the podcast circuit, since this topic is something very topical, very important, and Chris has now sort of cornered himself out as really one of the authorities to speak about it. And so if you're keen to hear another chat very similar to this, please look at my interview with Jos Benschop, who is one of the creators of the CD and someone at the cutting edge of this technical innovation since its inception. The link to that interview is in the description. But finally, to my ambition for the podcast, like I said last week with Angelica, I'm recording this introduction at the exact same time, but it's been quite a while since I've plugged the show, since most of the episodes recently have been specifically about the war in Ukraine. My hope with this podcast is to corner the podcast market for eclectic curiosities, whatever that means. It's not defined by anyone. There is no specific niche. When you're searching in the search function of your podcast, you can't search for eclectic curiosities and get a list. But that's my hope. That is the podcast niche that I want to corner. And the only way to get there, I can see at least, is to have more reviews and more interactions with these various podcasting algorithms. So yourself, your mates, your pets, people you work with, encourage them to leave nice, juicy, healthy reviews. I think that at this stage, at least, that's the best thing that you could do. So visit the website. It's in the description. It's the link at the top to Chris Miller. And, I just, that's my hope. That's my ambition for the show. What else can I say? All right. Well, see you next week. Cheers. Ciao.